welcome to today's lecture of our course Reasoning LLMs from Scratch. In the last lecture, we looked at a function which is called as advantage function. And what we saw was the advantage function denoted the difference between the state, the action value function, and the state value function, which is denoted by q pi of st comma at minus v pi of st. Intuitively, this means that how better or worse your current action is compared to the default behavior of the policy. For example, if you start with a state st and you have a number of actions to take from that state, and let's say your policy's default behavior at the moment is to choose this action which is known as A0. And then what you do is you look at all these other actions, which is A1, A2, and A3, and you make a table and try to see, let's say the value of A0 is, so this is the value function 50. And you try to look at the expected cumulative rewards for all these other actions. And let's say these are 30, 40, and 60. So the observation that we make is that for action A3, the expected rewards are higher compared to the rewards which the agent is expected to receive for the policy's default behavior. And thus we know that there is scope for improvement, which means that the current policy is not optimal, but there exists an action which is better than the current action which the agent is choosing for that particular state. And this intuition can be mathematically represented in the form of an advantage function, which is given by this difference. So the advantage function for all these different actions would be minus 20, minus 10, and this is positive 10. So the sign of the advantage function is telling us a lot about how optimal the policy is or how much scope there is for improvement. And that's why this is a popular terminology which is used in a lot of policy gradient algorithms. And then we looked at a method for estimating the advantage function as well, which is using the generalized advantage estimation, which is GAE. Remember, the advantage function is denoted by A of st comma at, and the most simple way to approximate this is by using a temporal difference target for the action value function. That is, we do RT plus gamma times value function of the next state. This is a simple way to estimate the advantage function, but the problem with this estimation is that it can be biased, uh, because we are only using one term for the estimation. It can be biased. That's why what we do is that we use composite returns. We use not just a one step backup that we saw here, but we use a combination of one step, two step, three step, up to an n step backup. And that is exactly what is done in generalized advantage estimation. But for the purpose of understanding, a broad level understanding of these two concepts is enough for us to move ahead to the next lecture. So now in today's lecture, we are going to understand about a technique which is called as trust region policy optimization. This paper came out in the year 2015, and from there on to 2025, all the modern developments, which include algorithms like PPO, GRPO, which is used in DeepSeek, all of these are built upon the derivations which were made in the TRPO paper, and it introduced a very important concept of trust region, which is at the center of all the algorithms that we are going to see subsequently. And that is why TRPO concept, or the understanding of trust region policy optimization, is going to be crucial for us as we move ahead to the next part of our course. Now, before we move ahead, I would like to emphasize that this lecture, unlike the other lectures that we have seen in this course, would be a little bit theoretical. That means that it would involve some amount of mathematics at the start. However, once you go past that mathematics, we will look at some intuitions to remember what all we have seen so far, so that even if later you forget all the mathematics, the intuition stays with you. Generally, what I have seen, that if we go through the mathematics, it gives us a fair amount of confidence. When we look at all these symbols, we don't get intimidated by them. So when you read this paper, or when you look at any other RL algorithm which comes out, you can see that, oh, there is a trust region here. I can see that because I remember it from either the mathematics or the intuition that I have built from this lecture. So the first part will be a little bit theoretical, but please stay with me because the reward is going to be pretty interesting later on as well. Okay, so let's get started. We are going to start with some notations first. So let's say we denote the performance measure of the policy as n of pi. Remember, we had a notation for this called j of theta, but the reason why we have denoted it now as n of pi will become clear shortly. And remember how g of theta was defined? It was defined as the cumulative expected rewards which the agent is going to get starting from the initial first state of the episode, which is denoted by S0. So essentially, what you do is that you add up all the rewards which the agent is going to receive in the future, and you take an expected value of them, which is the definition of the value function for a given state. So the only thing we have changed here from g of theta is n of pi. Now, what we are going to understand is, let's say that there is another policy pi dash. The crucial question that we will answer in this entire lecture is, for the policy pi dash, let's say I define the performance measure as n of pi dash. The question is, can we write n of pi dash in terms of n of pi, which means that I want to understand whether the performance measure has improved or not compared to one policy. So I have two policies, pi and pi dash, and since both of them are different policies, their performance measure is going to be different. Now the question that I am asking is that, can I write down the difference between these performance measure in terms of a simple mathematical equation? Uh, okay, so now with this question in mind, and with our earlier discussion of advantage functions, can you think of some kind of uh, intuition for this difference, or n pi dash minus n of pi? Can we think of what will this term be proportional to? So let's try to understand this, then we will get into the formula as well. So let's say this is state S, right? And according to the policy pi, let's say the policy pi tells me that I want to take action A1 for this state. Now, my policy pi dash tells me something different. My policy pi dash tells me that no, you don't take action A1 when you are in state S, but you take action A2. Now, the question that I am asking is, can we write down the performance of, so this is policy pi and this is policy pi dash. Can we write down the performance of the policy pi dash in terms of the performance of the policy pi? One thing I know for sure is that if the advantage of this action is positive, then it means that the performance of this policy is going to be better than the performance of this policy at this state. So basically, n of pi dash minus n of pi is going to be proportional to the advantage. Okay, so this is what my intuition says. My intuition tells me that if I calculate the advantage for a particular state and action uh, for the new policy pi dash, and if the advantage is positive for all the states, it means that my new policy is, of course, better than my old policy because there is a significant scope for improvement at every single state of my policy of the entire episode. So this is the intuition that I'm carrying with me as I'm going through my derivation, and there would be probably some kind of summation over here because remember that I am calculating an expected reward over all the different states of my episode, which means that I am starting from S0, but I am visiting, let's say, S1, S2, S3, and then this visitation is there for my policy pi, but for my policy pi dash, my visitation is completely different. It's S1, S2, S3, S4, dot dot dot. Now, the problem which I am facing is that, let's say I know my initial policy and I want to change from the initial policy to a new policy, but I do not know what the distribution of the new policy is going to be. We will look at this question a bit later. For now, we'll just focus on the difference between the performance measure of the new policy and the performance measure of the old policy. And at the moment, our intuition says that it's going to be proportional to the summation of the advantages calculated for all the states in the episode. Okay, so now we are going to look at this question. Can we write n of pi dash in terms of n of pi? And in the next two sections, we are going to look at a straightforward mathematical derivation of the difference between these two performance measures. Okay, so the first step, we write the performance measure as the value function of the initial start state of the episode, which is the expected value of all the cumulative rewards which I am receiving in the long run. So here what I am doing is R of S0 plus gamma times R of S1 plus dot dot dot. Now I do a mathematical operation here. I subtract from a value and I add that same value. So I subtract from V pi of S0 and I add V pi of S0. Remember, this expectation is taken over the new policy pi dash, but here inside the expectation I am subtracting and adding the same quantity. I can do that because this is 0 anyways. Now what I do is I write down this expression now, which is n of pi dash minus n of pi. For n of pi dash, I'll just simply substitute this whole expression at the bottom. So I substitute this whole expression over here, and this is nothing but n of pi. Okay, now what we do next is, next we want to take this expectation out, this expectation of over pi dash v pi of s0. So we do nothing but we take one expectation out. So inside the bracket we have only two terms, and we take this expectation out. Now when we take this expectation out, we see that this is expectation over pi dash v pi of s0, and that is nothing but v pi of s0 itself. And the reason is that there is one expectation outside over pi dash, but inside also there is another expectation. This is expectation over pi of all the summation of rewards. So this expectation is not going to create any difference, and this is equivalent. That's why the difference is going to be 0. And because of this, we can write down the differences of the two policies as expectation over the new policy pi dash of summation of the discounted rewards which the agent receives from time t equal to 0 to t equal to infinity, minus the value function of the initial starting state of the agent. This is our first step. Now we are going to look at another way of evaluating this same expression. So we are going to start with the advantage. Remember, a is called as the advantage function, a pi, and we have written this as r of st plus v pi of st plus 1. This is nothing but an estimate for the action value function q pi, which is what we saw at the start. If you look at this, we saw that there is a way to write q pi in terms of the temporal difference target, and we do that here. We write down q pi. Okay, so we write down q pi in terms of r of st plus v pi of st plus 1. Okay, now what we do is we take a summation of all of these advantages, and this summation is taken over from t equal to 0 to t equal to infinity. So here we have taken summation of t equal to 0 to t equal to infinity, and this same summation runs over all these different terms. So here we have multiplied the first term by gamma raised to t, second term by gamma raised to t, and third term by gamma raised to t. So here we are doing nothing but we have first written down an expression for the advantage estimate, and second we are doing a summation from time t equal to 0 to times t equal to infinity. Okay, now there is an interesting observation here. If you look at these two terms, sigma t goes from 0 to infinity, gamma raised to t v pi st plus 1 minus gamma raised to t v pi of st. So let's start from the first. For t equal to 0, this is going to be gamma v pi of s1 minus v pi of s0. Now for t equal to 2, this is going to be gamma square v pi of, for t equal to 1, v pi of gamma gamma raised to, okay, this does not have gamma here because we consider t equal to 0 as the first step. For t equal to 1, we have gamma times v pi of S2 minus gamma times V pi of S1. Now, what we see is that this is a telescopic sum, which means that if you add up all these different values together, you are going to get a summation which only consists of minus V pi of S0. And the reason why that happens is that if you look at, okay, so there was one error in this derivation. What happened was that in the first step, we did not consider a gamma over here. So there is a gamma here because this is the way we write the temporal difference target for the action value function, the immediate reward plus the discounted value of the next state, which is r of st plus gamma times v pi of st plus 1. Now, here, because we have gamma, instead of gamma raised to t, this would now become gamma raised to t plus 1. Now, if you look at these expressions of the summations, let's look at what that would be. So, for t equal to 0, for t equal to 0, the first term is going to look like gamma times v pi of s1 minus v pi of s0. For t equal to 1, the second term is going to look like gamma times 2, gamma raised to 2, v pi of s2 minus gamma times v pi of s1. For t equal to 2, the term is going to look like gamma raised to 3 v pi of s3 minus gamma square v pi of s2. Now, if you add up all these terms, you see what happens is all these terms cancel because they are one and the same. And the only term that you will be left with is this minus v pi of s0, which is exactly what we have written over here, minus v pi of s0. So this is called as the telescopic sum. It is a technique used in a lot of mathematical expressions to simplify the expressions. So if we use the telescoping sum over here, all these terms cancel and only thing we get is minus v pi of s0. Now look at the first expression that we had got in this bracket. This is exactly same as this, which means that we can now write the difference between the advantages n of pi dash minus n of pi as the expected value over pi dash summation of all the discounted advantages. And now we take this negative sign to the right of this expression and we can express the performance measure of the new policy in terms of the performance measure of the old policy. It turns out that the performance measure of the new policy is the performance measure of the old policy plus the expectation of all the summation of the expectation of the summation of all the discounted advantages which the agent sees. And this is quite similar to our intuition over here. If you look at this figure where we had drawn our intuition, we had said that the performance measure of the new policy is going to be different than the old policy, and this difference is going to be proportional to the summation of all the advantages which the agent is going to get in the future. And this is exactly what we get over here. Now, even if you have found the mathematics somewhat tedious or complicated, forget the section before and try to focus your attention on this expression, which tells you how different is the performance measure of the current policy compared to the performance measure of the previous policy. And this difference is going to be uh, understood by taking your agent, going over the entire episode, and then for every state of that episode, asking the question, what is the advantage which I am receiving in this state? And to calculate the advantage, what you do is that you take actions as per the new policy, but the value function you have to include as per the old policy. So you subtract the action value function, and you subtract the action value function and the value function for that particular state. So just close your eyes and imagine an agent traveling through a lot of states. So let's try to visualize this. Imagine an agent which is starting from state S0, then the agent moves up, goes to state S1, then goes to state S2, traverses the environment. And for every state, the agent takes actions. So this is the action sphere for this state. The agent can take many actions, and the agent chooses one specific action as per the new policy, pi dash. And now, what we do is we take this new policy, we calculate q pi, and we subtract it from the value function which is calculated according to the old policy. This is how we are going to get the advantage, and we are going to understand how better or worse is the new policy compared to the old policy. And we are going to add this up for all the states which my agent is going to see in the future. Once you have understood this visualization in the mind, this equation will be fairly easy to remember in the future as well. So if the new policy has non-zero expected advantage at every step, then the policy is guaranteed to improve. And this is exactly what we do in the policy iteration step of dynamic programming. This was the fourth lecture of our course, and we had done the same thing. Now we are just writing that same thing in the form of an equation. So in dynamic programming, remember we had a policy iteration step where we had to look at the current policy and we had to understand, okay, I have calculated the value function for my current policy. Now what I'm going to do is that I'm going to go to all my states and I'm going to see if is there any action which gives me better value than my current value function for that state. And if I find some state like that, I am immediately going to change the policy of my I'm going to change my old policy and I'm going to change the action which my agent took for that state to the new optimal action. And I will do this again and again and again till the time the value function of my current policy is giving me the most optimal expected rewards at all the states. There is no action which gives me better rewards than what my current policy says. So essentially, we were calculating the advantage function only. We were taking the difference of the action value function and the state value function. But at that time, we did not have this terminology of advantage. But we are doing that anyways. Okay, so now one of the issues with this method is generally when we are doing some kind of an iterative algorithm. So in the iterative algorithm, I know that this is the trajectory which my agent has taken, right? This is the old trajectory. And I am going to now change my policy for all these states in such a way that the new policy has a better performance compared to my old policy. Now, our formula tells us that you first have to calculate where the agent is moving under the new policy. And then only then you can do a cumulative summation over all the advantages which the agent sees for all these states which it encounters in the new policy. So the green one represents the old policy and the red curve represents the new policy. So when people wrote down this formula for the performance measure of the new policy in terms of the performance measure of the old policy, they thought that if we want to write this as an algorithm, the problem we will face is that we don't know which are the states which my agent is encountering in the new policy. I do not know these states. All I know are these green states which my agent is has already encountered in the previous policy. So, can I use the information of the states from my old policy itself instead of using the information of the states from the new policy? That might look tricky because the formula clearly states that the expectation is taken over pi dash, which means that we have to visit all the states according to the new policy. To understand how this change from the or using information from the old policy, we can update this expression and change it so that we don't need to know the state distribution under the new policy, but we only need to know the state distribution under the old policy. We have to tweak this equation a little bit and we have to bring in all the states which the agent is visiting. So here in this equation, you do not see any states, right? But essentially, because you are following a policy, the agent is visiting a certain number of states while interacting with the environment. So there is an alternative way of writing this same equation, which we are going to look at below. Now, this is the expression that we have, which measures the difference between the new policy and the old policy, which is the summation of all the estimated advantages at all time steps. Now, what we do is we keep this term as it is, but what we do is we replace this expectation as a summation. So, this is a common trick which is used in probability where if you want to replace expectation by a summation, what you do is you first uh, see the probability of visiting all these states. So, probability that the state visited under the given policy, and then sum them up over all these states, and then you sum this up over all actions as well. So essentially, we have replaced this expectation by two summations. One is the summation over all the states, and second is the summation over all the actions. So, a very easy way of understanding this is that what do we want to do here? We want to add up the advantages for all the states and actions which the summation, which the agent is encountering. For that, to know this, I first need to know which all states my agent is visiting. That's why the summation comes up. Probability of the state visited is equal to S given the policy pi dash. Okay, so this is the states which you are visiting. Now, not just visiting each state, but for every state, I have different actions which I can take, right? So, which action I will choose? For that, we need to do summation over all the actions. And here is where the policy comes in pi dash of a given s, and then the expression that you had. So, gamma raised to t times advantage of by S comma A. So essentially, this expression is nothing but uh, expanding the expectation operation to include all the states and actions which the agent is encountering. It's quite intuitive. And then we do a simple transformation. What we do is this gamma raised to t. We look at this expression gamma raised to t times the probability of visiting each state under the policy, and this is nothing but the state visitation frequency, which is denoted by rho of s. Let's try to understand what is the state visitation frequency. So let's say you have all these states s0, s1, s2, dot 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 sn, and every state has a different frequency of visiting. So you calculate how many times the agent has visited each state, and you add them up, and you sum and you divide them by all the states which the agent sees in the episode. So here I can see that S2 has the maximum probability. So rho of S, which is the state visitation frequency, is actually given by probability of S0 equal to S plus probability of S1 equal to S plus probability of S2 equal to S dot dot dot. It is essentially this curve, and we add a gamma over here because it tells that the state visitation frequency is discounted by the factor gamma. So now, with this modification, you can replace or you can update the performance measure of the new policy in terms of the performance measure of the old policy by using this expression, where you see that performance measure of the new policy is equal to the performance measure of the old policy plus the state visitation frequency. What is the distribution of all these states? Which states are visited more, which states are visited less? All that information is coming into this term. And then you multiply it by the probability of choosing each action for that state, which is given by the policy, times the advantage. So we have now removed the expectation, and we have a term which is helping us to understand how much frequency each state is visited. So this term essentially captures this distribution which we are talking about over here. Okay, now once we have written this, the problem which we discussed before becomes apparent. Why it becomes apparent is because we do not know the state visitation frequency for the new policy. The only thing we know is the state visitation frequency for the old policy. As we see from this graph, we know the state visitation frequency for the old policy, which is marked in green, but we do not know how many times the agent is visiting each state for the new policy. That information is unknown to us. But as you see in this expression, that information is required. Without that information, we cannot calculate how better or worse is the performance of the new policy compared to the performance of the old policy. So what people do is that they simply substitute rho pi of s instead of rho pi dash of s. So we take the liberty of saying that okay, this is the actual equation, but we are going to modify this equation and we are going to replace the visitation frequency, or we are going to assume that the agent visits the states according to the old policy. The agent can take actions according to the new policy, that is fine, but the agent visits states according to the old policy only. And then the new performance measure is given by this n of pi plus sigma rho times pi of s, which means that you are going to look at the states which the agent is distributing or visiting under the old policy. So, what we have done in this last section is that we have looked at the expression which told us the performance measure of the new policy in terms of the performance measure of the old policy as a summation of expectation over all advantages. Then we saw that, okay, let's break that expression down so that we remove the expectation and replace it by a term which told us the frequency of the agent visiting each and every state. Now, once we got that expression, it became apparent to us that we do not have this term with us. We do not know which state is the agent visiting for the new policy, and we say that, okay, fine, we are going to use the distribution which we know from the old policy itself, and we are going to replace that term in this expression. And then we get a new performance measure which is denoted by L pi of pi dash, where pi denotes state distribution under the old policy, but performance is calculated for the new policy itself. So let's try to understand this in terms of a diagram. Let's consider only three states. Let's say this is S0, S1, and S2. This is the old policy. Now, what we do is that for the new policy, to calculate the performance of the new policy, we assume that the agent keeps visiting these states. So the distribution of the states is the same as that of the old policy, but the action which the agent takes for this state is going to be according to the new policy. If the action is same as the old policy, then we'll get the same trajectory as the old policy. But here the action is according to the new policy. So actions are taken according to the new policy. And we look at all these actions and we calculate the advantage estimates for all these states, and we do a summation of all of them. And this is how we estimate the performance measure of the new policy in terms of the performance measure of the old policy. So now, once we have understood how to represent the performance measure of the new policy in terms of the performance measure of the old policy in such a way that the expression can be calculated by us, we can move ahead. Remember, the objective is to calculate the best performing policy out of all the policies, and that is why we are writing this expression. We want to get better and better and better, and we want to calculate the optimal policy for the equation for our agent. Now, there is one expression that we can write, and the expression is given by uh, this is the performance measure of the new policy, the actual performance measure, and this is the approximate performance measure. So, the actual performance measure of the new policy is greater than or equal to the approximate performance measure minus a coefficient into the KL divergence of both the probabilities. Now, KL divergence is a measure which helps us understand how different two probability distributions are from each other. For example, if you take, let's say, two Gaussians, these are probably similar, but if you take this probability distribution and compare it with this, the KL divergence is going to be higher because the probability distributions are very different from each other. So this is an operation which helps us calculate how different are the distributions from each other. Now, this theorem tells us that the actual performance measure of the new policy is greater than equal to the difference of the approximate performance measure of the new policy with the state distribution from the old policy, which is denoted by pi, minus a coefficient times the KL divergence between the old policy and the new policy. The proof of this is complicated, and we are not going to go into this proof at all. It is not required for the purpose of understanding this content. Okay, so now once we have this expression, we are going to study how can we optimize our policy such that we move towards better and better and better policies. And for that, we are going to let's look at an intuition first to understand that better. So okay, so let's say that our goal is to maximize this function, which is f of theta, and we start with this point P, which lies over here. Now, from just a visual inspection, we know that this is not the optimal parameter for theta. The optimal parameter for theta lies somewhere here. So we need to ascend this curve. We need to move towards the top of this mountain, towards the peak of this mountain. So, but the problem is that we do not know f of theta beforehand. We do not know the function f of theta. So then what do we do? How do we calculate this peak if we do not know f of theta itself? How do we calculate the gradient even if we were to apply the gradient descent algorithm to traverse the peak? We do not know the function. So what do we do? Well, we calculate a simpler function and we try to maximize that. So what we do is, if you look at this red function over here, this red function is something we know, and this red function is always going to lie below the black function. Okay, so this red function is such that it matches the black function at one point and it's always below the black function. So I can estimate the red function now. So let's say I can estimate the red function, and what then we do is, instead of calculating the maximum of the actual function, we don't know the actual function, we calculate the maximum of this red function, which we know is this, and the parameter associated with that is theta 1, and then for that theta we calculate what is f of theta 1, and we ascend the curve. So you can see that I am, without even knowing f of theta, I am moving towards a parameter which has an improved value for f of theta. Similarly, we do the same thing for the next point. For the next point, we again construct this function, this approximate function, which is given by this blue curve, which is always less than the black curve, always touching the black curve at one point. We calculate the maximum of this function. We see which point is giving me the maximum. We move from the old version to the new version, old parameter to the new parameter. So initially we moved from theta 0 to theta 1, then we moved from theta 1 to theta 2. So what we have done here is that without knowing the actual function, we have constructed a new function which is called as the surrogate function. And at every step, the surrogate function is less than the true function. So instead of maximizing the true function, we are simply maximizing the surrogate function. And through this process, we are moving towards better and better estimates of our parameter theta. Now, this is exactly the same what we are going to do with our policy. So, let's say this is the performance measure of our policy, n of pi dash, and on the x axis we have a policy parameter theta, and I start with the point P. So my performance measure currently is not the best. There is a huge scope for improvement. But the problem is that I do not know enough pi dash because state distribution is not known, as we had looked at later, as we had looked at before. the state distribution is not known. Now the state distribution is not known, so we do not know this function n of pi dash. But let us do our best. Let us replace the state distribution of the new policy with the state distribution of the old policy and construct a surrogate objective function denoted by L of pi dash, which is the same expression we had looked at mathematically, but right now we are trying to build an intuition. So just forget the mathematics for a moment. So we are going to construct a new function, which is so this new function is actually L pi dash minus CD KL pi of pi dash, pi comma pi dash. And this new function is, we want this new function to be such that it is always less than the true function. So it's always here at the bottom of the true function, so that instead of optimizing the true function at every parameter, all we do is we optimize the surrogate objective function. And this expression satisfies that it is less than n of pi dash as we looked at before. So if you zoom in on this, you know that this is the true function and this is our surrogate objective function. And at every step of the way, if we maximize the surrogate objective function, we are going to move towards the direction of maximizing the true objective function. So all I will do is I am at point P. I will construct a surrogate objective at point P, calculate the maximum of that, move towards the next point. I'll again find the surrogate objective function for the next point, calculate the maximum, move towards the next point, calculate the surrogate objective function, etc. So essentially, I will throw away this n of pi dash and replace it by this surrogate objective function, which is given by L pi dash minus C times the KL divergence of the old policy and the new policy. So our algorithm for the policy evaluation then becomes very simple. Once we understand that this n of pi dash is always greater than this surrogate objective function. Now we understand why this equality is so important. This equality is important because we can construct a surrogate objective once we have this equality. And once we construct the surrogate objective, we can maximize that surrogate objective. And that will maximize our true performance measure of our policy. So this is the fundamental concept which you need to understand. Uh, and this concept is something which people take granted sometimes when they discuss about different policies, different algorithms. But there is a very robust theory which brings us to this concept. And that theory says that, okay, it's fine even if you know, even if you don't know the state distribution of the new policy. If you know the state distribution of the old policy, can you construct a function which is always less than the original objective function, which matches the original objective function at one point? Now, the question is, does it match this function if pi equal to pi dash? Well, if pi equal to pi dash, both the distributions are the same and KL divergence is equivalently 0, right? And if pi equal to pi dash, then L pi dash is exactly the same as n of pi dash. So yes, they do match. So this surrogate objective matches exactly with the true objective at one point. And we have now constructed this surrogate objective function. So now in the remainder of this lecture, all we will do is we will try to optimize this surrogate objective function. So the policy looks simple. Initially, we will initialize the policy pi 0, which can be a randomly initialized policy. Then what we'll do is we will calculate all these advantage values for all the states and actions of that episode, for that policy, and then we will find the maximum of this, and that maximum will be the next iteration of our policy pi 1. Then we will again find the maximum of this and move to pi 2. Then we'll again find the maximum of this, move to pi 3. This is exactly the same that we have done over here in this diagram. At every point, we are calculating the maximum of this surrogate objective function and moving towards the next better policy. So this is the algorithm that we will use, and which is written by which is written in this expression. In summary, we want to do the following: we want to maximize L pi old pi new minus CDL K max pi old comma pi new. The expression in the bracket measures how different is the new policy from the old policy. This is the expression which is being talked about here, which is the KL divergence. Okay, so now once we have understood this equation that we want to maximize, we will now come to an important part of this lecture which will help us understand where does the term trust region come from? Why is this algorithm called trust region policy optimization? Well, the roots of this can be actually traced to this expression. So, this is the KL divergence, which is the divergence between the old policy and the new policy. So, if this divergence becomes very large, this whole term is going to be small. So, we don't want that since we want to maximize this term. So, this maximization or this objective function does not allow us for a large update in the policy. It is essentially constraining my policy update. It is telling me that okay, if this is your pi old, there is only a limited radius in which you can move. You cannot move outside this radius, because if you move outside this radius, then this term is going to receive a big penalty because there is a negative sign over here. So, in other words, this expression itself is like it's adding a trust region on top of your old policy. So, this is the trust region which does not allow your policy to move very far from the old policy. So, what people do is that they decouple this expression into two separate expressions. The first is uh, we will just say that we want to maximize the first term, which is the L pi old pi new, but we constrain the KL divergence of the old and the new policy. So we say that the maximum KL divergence of the old policy and the new policy is less than delta, where delta is called the trust region. So the trust region imposes a constraint that the KL divergence is bounded for all the states, not allowing the new policy to differ from the old policy. So if you are here, this is the current policy parameter. The TRPO step will only be restricted towards this trust region. It won't go beyond that. Whereas the vanilla policy gradient descent or the vanilla policy gradient approach, it does not have any constraint, so it can go up to this also. Why is this good? The reason it's good is because if you look at most of the large language models, the base model is already very good. Now reinforcement learning is used to align the model with human preferences, and if the deviation of the new model is too large from the old model, it might lead to some unintended consequences or the model failing in a lot of prompts. That's why there is a trust region which always helps, which allows us to make sure that, okay, we want the model to get better and better, but we don't want it to move so much from the old policy. And vanilla policy gradient suffers from this because at every step you are making an update based on grad pi divided by pi, remember from the previous lecture. Now for this each update, you have a lot of variation. Sometimes the updates are big, sometimes the updates are small, so there is a big variability. Now this approach, it reduces the variance also, because you have a restricted zone in which your policy is allowed to move, and this zone is given by the zone marked in this blue shaded region, which is the delta. That is the reason the whole algorithm has the name of trust region policy optimization. So up until now, what we have covered is that firstly we looked at how can we write the performance measure of the new policy in terms of the performance measure of the old policy. Why do we do that? Because we want to write a policy iteration update that moves us towards better and better policies. The problem we faced with that is, uh, okay, we have now a policy iteration function where it tells us how different is the new policy from the old policy, but we cannot estimate that function because we do not know the distribution of the states under the new policy. So what we do is we calculate the distribution of the states under the old policy only, and then we construct a new objective function that we want to maximize. And this new objective function is such that it is always less than the original objective function, and it matches the original objective function at one point. So now what we have is, we have an original objective function that we want to maximize, but we cannot estimate that because we do not know the distribution of the states under the new policy. So we construct a surrogate objective which always remains less than the true objective function, and we maximize that surrogate objective function at every single step, and we move towards better and better policies. So you will see me using the word surrogate objective more in the subsequent lectures. I want you to refer to this understanding when I say that. And how does the surrogate objective function look like? The surrogate objective function looks like this. It is the difference of two terms, term 1 and term 2, where term 1 is the same as the true objective function. The only difference is that the state distribution is calculated under the old policy, whereas the term 2 is the KL divergence between the two old policy and the new policy, which helps us understand how different are the policies from each other. And there is another way of representing this same is by just including this in the objective function and then including the KL divergence as a constraint. So this becomes a constraint optimization problem because we have a expression that we want to maximize under a specific constraint, which tells us that the new policy cannot move away from the old policy that much. It can only move away within a specific distance, which is denoted by delta. Now, in this lecture, we have looked at some new notations, which is L pi, old pi, new, which is the surrogate objective function now, because the KL divergence has been moved to the constraint. Then we looked at KL divergence, it is denoted by DKL. Maximum denotes, we look at KL divergence for all the states and then we take a maximum out of that. In practice, there is an average term over here, but we are neglecting that, choosing to neglect that because we want to focus on the main concepts and developing the intuition behind TRPO and not get bogged down by too much of mathematics, because really the intuition is the key here, and uh, it's simple to understand the intuition. Now, as I said, this paper came out in 2015, and it was heavily based on this concept of trust region, which allows us to make updates in a reasonable fashion. The concept of surrogate objective function has been existing before since 2002. There is a famous paper by Kakade, I think, which came out during that time, which also talks about these concepts. But in the TRPO paper, the formalization and the introduction of the trust region was something unique, which has become the norm even in PPO and GRPO, which is used in DeepSeek. Uh, Thank you very much, everyone. This brings us to the end of this lecture. In the next lecture, we will look at how is this function or constraint optimization function in TRPO actually solved. Thank you.